Alright, I've been thinking a bit today about the next phase, the next stages of the design. I was just talking to a friend of mine about this, and basically the constant consumption of my generator is always pretty low. It's around, it can be anywhere between 100 and about 180 milliamps up to 400 milliamps. I mean, I've got the timing for the drive system really well timed now. The only issue really is dealing with the drag due to loading factors, and that's the next phase, and that's what I'm thinking about. So basically, it's a sub circuit which is required. Yeah, so more circuit boards. So I mean, I've got this circuit I haven't even put on a breadboard yet, and I'm thinking, well, maybe I shouldn't put it on the breadboard yet. Sorry, on a circuit board yet, because I'm going to need a separate circuit, something that will actually pulse, and I need to really use the sense coils, the trigger coils, the existing ones, and I need to tap some of that signal off. So it makes sense if I could build it all on one board, really. So I also wanted to show how long it takes this thing to stop when I turn the power off, because it really is very low drag. It has very little cogging at all. There's virtually none. If I can get the RPM meter in the shot as well. Oh, actually, I'll bring the RPM meter over here just a minute. It's probably better if I... Oh, I've got batteries attached to it now. Just a minute. I connected some batteries onto the RPM meter, so I didn't have to run it off my main power supply. Right, let's just stick these. Let's stick the RPM meter down here if I can get it on the table. It doesn't want to sit still. Right. I'll try and get it there. Right, so the RPM meter is there, and basically this thing takes forever to stop when I turn the power off, because there's very little cogging. I mean, I can flick this with my finger to start it. I'm going to show you that actually. So we're at 270 milliamps, 270 milliamps, and I'm going to turn the power off. Initially there's a bit of a zzz because there's little residual power in the circuit, but it makes a bit of a noise, and then there's no cogging at all. So let's just turn it off. Right. Right, it's stopping. It's stopping. Now it's bouncing now. So basically when it gets to that point, it starts to bounce a little bit. So how easy is it to turn this? Well, I can move it with my finger easily. Little finger, look at that. I mean, if I can get the camera on here, there's very little cogging on there, and there's actually a lot of coils and ferrite around it as well. So I wanted to just show you this, because it just turned very easily. I could even turn it with a spindle here. Stopped. Turn it. So I'm not using leverage to my advantage. It turns very easily. So yeah, a lot of this stuff I see on YouTube, they grab it something, they grab the rotor and they go because he can hardly move it. Well, this thing turns easy because the design of the magnets and the concentrics and everything else, there's very little drag on it. And don't forget there's 3 sets of ferrites in there now. There's the dry ones at the bottom, then there's the generator coils here, and these ferrites go all the way to the middle core, you know, a whole stack of ferrite rings. The way that it basically works is that you divert the flux so that it opposes itself, and it pushes back on itself so it doesn't attract so much. That's the principle I'm using. For example, I did explain this in previous videos, but I'm just going to go over it one more time. Right, some magnets. A lot of strong neodymium magnets. Now, if you get a nail, you stick one nail on the magnet, what happens? The magnet, the nail will stand straight up, but you get another nail, and you basically stick that nail next to the first nail, and what happens? If you push those two together, they're going to repel each other. They actually repel. They don't want to come together. If you push them together, they push apart. So what we're doing, basically, if I put them on the edge of the magnet, this is probably not, I'm using too many magnets here actually, to be honest with you. It's ideally best if I just use one I'm trying to get these off, and I'm using too many magnets actually to show you this properly, because it doesn't work so well when you've got a load of magnets. You really need just one magnet to show this properly. I can't get it off. God, these are freaking strong. Right, let me just stick it on the fire so it doesn't fly it back into my hand again. Right, one magnet. It works better. It depends on how long the magnet's array is. Now, a nail, 2 nails. Oops. If I can do this right. Right, you see the other nail fell over. It didn't fall over because of gravity. It fell over because the magnetic flux is pushing it away. Now, if you understand, if you study flux, you'll understand that you can use magnetic fields to basically cancel each other out. Now, if I put this nail next to that other nail, and I try to move that nail towards that other nail, it will push the other nail away. Watch very carefully. Watch very carefully. I'm not touching the second nail. I'm only pushing one nail, and the other nail wants to move away. You see that? Oops. It spun around. You see that? Now, you can use that effect using a toroid. Right. So I'm pushing this nail. It doesn't want to go. These 2 nails will not come together because the flux is like. It's a Lycan flux field. So basically what happens is they push themselves apart. Now we can use that to repel a rotor, to repel against the actual inductors that we're sending the flux down, so that we don't have too much drag. That is the principle that I'm using. Now if I get the longer the magnet array is, the more drag. That's the problem. Now, the magnets that are set up in, let me just try and show you this on the rotor, the disc. Can't get off. Right. Everything's stuck to this thing. Right, get that off. Right. The drums I've got in there in my device anyway, they're basically 3 sets all together, and they're all the same pole, so they're actually basically pushing the flux is pushing it against itself. So this particular field, if I stick that magnet there, is the same field as there. Look at that. Look at that. The nail fell over. Interesting, right? You see what happened then? Get this nail. Put this other nail right next to it without touching the first nail, and watch what happens. Oh, let's push it together. It doesn't want to go. It doesn't want to go to the other nail. Right? These two nails do not want to come together. You would think, ah, that's strange. No, it isn't. It's the flux is pushing itself apart. I'm trying to show you this and hold the phone at the same time. Right, the first, I'm going to put it dead straight. Right, push this first nail. Now look, it won't go. It's going to flip over, or the other one's going to flip over. One of them is. When I get too close, look, it's pushing the other nail away. Look, it moved. It spun around. So we can use that effect to cancel the amount of drag, which is why I'm using donuts, toroids, because it does the same effect. When you bring a toroid towards these magnetic fields, there's very little drag on them because the flux is pushing back against it, so it doesn't have much attraction. And I've showed this in previous videos, but people don't always watch all my videos. They tend to watch the latest ones, and you'll have to skip back and see all the testing I've been doing with it, but I'm just showing the basic stuff about it, really. I've got a toroid handy, really, but it's just, yeah. Anyway, you've seen the principle anyway. I haven't got a spare toroid handy I could show you that with, but there's very little attraction. But normally when you bring something like a ball bearing, it will just fly straight at it. So what I've got is a combination of ball bearings inside the toroid. So this ball bearing will fly at this thing. It will really stick really well, right? And it sticks to the point where it'll lift it off the thing. But when you put the toroid above it, it has a lot less attraction. It actually pushes back quite a large amount, really. So anyway, yeah, I want to show you how easy it was to stop this. And I did show you, I did explain that this is possible to start this. Let me just turn the juice back on. I can start this just by flicking it. It's not as sensitive at the moment because the way I've got it set, but you see what I mean? I can flick it with my finger and it'll start up once you get it going. It accelerates pretty fast, and it's only using 330 milliamps right now while it's accelerating. Let's just try and slow it down. While I'm slowing it down, the current has gone up to 450 milliamps. That's because it never goes that slow normally. It's got quite a bit of torque actually. You can see how fast it picks up speed. It's already up to nearly 4,000 RPM. But under maximum load, let's see what load have I got on here right now. About 100 milliamps output, roughly. Well, let's take the load off it. Right, I'm disconnecting the. Oops, my meter's falling over. Let's take the load off it and see how fast it goes. And current consumption. I haven't done this test before, so I'm showing you it now. Almost at 6,000 RPM at 200 milliamps. Vibrating a bit. I don't like it when it starts vibrating. Put the load back on. Right. It shot up to 200 milliamps just then. It's dropping again now because we've still got the problem of drag to solve. Anyway, that's just another little video because I don't think I really showed you it starting up and how long it takes to stop and everything. Anyway, that's all for now. As I say, I'm thinking about a sub-circuit which I need to design and think about that. Right, so don't expect anything quick soon, because I'm going to spend a couple of days thinking about that, because I've got to work it out in my head. I'm not good with math, so I have to try and visualise it, you see, which is a bit of a nightmare. So yeah, it'll be time for a visual inspection as well at some point of my rotors, which means dismantling it. I am planning on redoing the wiring loom for it, making a nice wiring loom. So at some point, I'm just gonna have to strip the wires off and take it apart and do a visual inspection on my rotors to make sure there's no cracks or anything. And if there are, I need to repair them with acetone and bond them all back together again. But I don't think there is. But the vibration issues do concern me a little bit sometimes, so I need to check on that, just to make sure there's nothing flaky, and if there is, patch it up with some, bond the plastic back. But it should be fine, because the other ones are fine. I've got another rotor here, which is I made at the same time as the other ones, and treated the same with acetone. And this one's got no magnets in whatsoever. It's just empty slots. And this one's not developed any fractures or cracks. Mind you, it's not under any stress. So, but yeah, I keep this one as a reference, really, to understand and know what might be happening to the ones in there. And then there's my other one, which is on the stand with the magnets in. I also keep that really as a reference at the moment to see if there's any cracking or anything. But there shouldn't be, because these things are really, really tough. They're really solid. And when I put the magnets in, I use acetone slurry, which set rock hard. And I did the same principle on the ones that are in there in the device. So there's no reason why there should be fracturing or cracking or anything. But I might do some tweaking on the balance as well. I might actually tweak the balancing on the ones in there sometime. Take them out and rebalance, because what happens is they dry out. Right? As they dry out, the balance change, the weight shifts. You get a little bit of a weight distribution change as the slurry stuff dries out. So I might have to rebalance those that are in there, but I don't know. We'll have to find out at some point, I suppose. I really don't look forward to taking it apart, but it's important for safety, to inspect. Even aircraft get inspected. Anyway, that's it for now, I think.